Hello students, welcome back. In sections 1 and 2, we studied the construction of numbers, the very definition, and some further classification, some arithmetics, ordering. We did various things. Now let's focus upon one system at a time. First, the integers. The properties of integers can be classified kind of like this. First, algebraic properties, those associated to algebraic operations, addition and multiplication. And order property, those related to inequality. And then inductive properties, we're going to talk about this a little bit later, that's the hardest one. First, the algebraic properties. We have all those typical algebraic rules: associativity, commutativity, identity, and inverse for addition. Similar thing for multiplication, but no inverse in general. For rational numbers, yes. Integers in general, no. Distributivity, all right. And then one interesting property here, no zero divisor. AB is 0, then either A is 0 or B is 0. There's no way I'm going to get 0 by multiplying two non-zero integers. So both A and B are non-zero, then A times B should be non-zero as well. And it's contrapositivity here. And finally, the cancellation rule. If A is non-zero, then I can cross out, and we get B equal to C. Well, in rational numbers, these are all trivialities. I mean, here, I can just divide by A, right? Indeed, that's the proof. Divide by A, so that we have 1, 1, so we get the crossing. And we can do that because A is non-zero, so 1 over A exists. Yes, we can use rational numbers. Even though we used the rational numbers, we came back to the integers, so it's okay. How about this one here, zero divisor? Again, we can use rational numbers. If A is non-zero, then I can divide by A, so we get B equal to 0. If B is non-zero, then I can divide by B, so I'm going to get A 0. Indeed, that's the proof. A is non-zero, and you divide by A, so we get B equal to 0. If B is non-zero, then I divide by B, so A is 0. Now, if you want to have a proof without Q, you can study proof 2. Also this one as well. A bit too advanced, so I'm going to skip those. Now, are they necessary? In set theoretical point of view, yes, because if you are to define everything, as a matter of fact, you have to establish all those properties in Z first, and then use those to define everything in Q. So you cannot actually use vice versa. Z has to be done first, and then Q. So you cannot use Q to prove anything in Z. And then there are some other aspects that are to be covered in abstract algebra, but getting too deep, so let's stop there. Order properties. C is linearly ordered or totally ordered. First, trichotomy. A is less than B or greater than B or equal to B. One and only one of those three must hold. Transitivity. A is less than B and B is less than C, then A is less than C. These two yields Z is linearly ordered. That is, you can arrange all the integers on a line. Not only that, Z plus is well ordered because Z is discrete. Every subset, every non-empty subset has a minimum. And then Z minus is also well ordered in reversed order. You have to reverse the order. So every non-empty subset has the maximum. And if you have any bounded subset of Z, then both minimum and maximum must exist. Putting these two properties together. That's a bit too trivial, so I didn't write it here. Now the ordering preserves addition and positive multiplication. You can add the same thing. You can add the same positive number. If you multiply a negative number, then you have to flip the direction of the inequality. Okay, that was easy. Now, inductive properties. This is going to be a bit challenging. First, from the construction of W, Q is 0, so we are starting from the very starting point, same as W. And then let's suppose we have this. N belongs to Q, then its successor, N plus 1 belongs to Q. Then Q covers everything. Why? This is nothing more than a successor operation. N generating N plus 1, this one. And that's precisely the way we can construct the entire W, starting from 0 and successor, 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 successor. It'll cover everything. Q also starts from 0 and the same way, so Q will cover everything. See this? Okay, next. How about this? N is a subset of Q, then N belongs to Q. What do you mean by N is a subset of Q? Remember the construction of the whole number. N is, as a matter of fact, N is defined like this: 0, 1, 2, and so on and so forth, up to N minus 1. So N is a subset of Q means all these numbers less than N belong to Q. Make sense? N is a subset of Q means all integer, all whole number k less than N belongs to Q. So this expression here and that expression there are the same. You see? N is a subset of Q means that. And then, of course, we can go back to the construction of W. You see, it is defined recursively like this. Each N is all those whole numbers up to that point. That's precisely this one, starting from the same place 0. So naturally, it'll cover everything. So Q is equal to W. All right. What do they yield? They're going to yield these two. The first one is a bit easier, so let's consider that one first. Let Q be a truth set of a certain predicate Pn, or equivalently, Pn is a condition for Q. Then N belongs to Q means N belongs to a truth set of Pn, so Pn is true. N plus 1 belongs to Q means Pn plus 1 is true. And Q and W are the same. Pn is always true for all whole numbers. So the base case, true for 0, and the inductive hypothesis, if Pn is true, then Pn plus 1 is true. With these two, we get this conclusion, true for all. This thing is called the induction principle, the standard induction principle. Now, how about the second? This one, N is a subset of Q, as a matter of fact, can be rewritten like this. K belongs to Q for all whole number less than N. And then you can set P of N as the condition for set Q, or equivalently, Q is a true set of this predicate. Then we have the base case, true for 0. And then for any whole number less than N, true for Pk. So Pk, so this one here corresponds to this. So true for all k less than N, then true for N. From these two, we get true for all. This latter one is called the strong induction principle. Both are induction principles, but this one is standard, this one is strong induction. The standard induction follows from successor operation. The strong induction comes from the recursive definition. So they're both coming from the definition, the construction of W, so they're both true. But if you cannot go back and recreate all the construction and everything, well, you can forget about those and remain just these two. Standard induction and strong induction. Everybody should be very, very comfortable with standard induction already as a prerequisite. For strong induction, well, it must have been covered in the Introduction to Proof course, yes, but probably not everybody is comfortable. So I'll give you a lot of hints and help whenever a strong induction is needed. But for standard induction, I do require some prior knowledge. Okay, all right. Those are induction principles. And that's how they are connected to the construction of integers. Let's see, do I have some more time? Okay, let's talk about rational numbers just a little bit. Algebraic properties, yeah, pretty standard. Order properties, yes, the same. The same. Not well ordered, okay. And there are some other properties. Q is densely distributed between any rational numbers, any pair of rational numbers. There is at least one rational number in between. In particular, we can take a plus b over 2, half of those, so half the distance, right in the middle, the average. But that's not the only one. There are many, many more. You can do it like this. Divide 2 to 1, or 1 to 2, or divide 3 to 2, or divide 3 to 8. There are many, many more, infinitely many more. So don't get an illusion that the average is the only possibility. There are many, many more. Finally, Q is countable. Well, I got this from the textbook. Following the sneak path, you can count everything, skipping some fraction if that's already counted. First, second, third, fourth, fifth, and so on and so forth. Consequently, Q is countable. There's a one-to-one correspondence between N and Q. Okay, so much for rational numbers. As for the properties of real numbers and complex numbers, I don't think they're going to be necessary for this course, so well, okay, I'll talk about it as an optional video, but they're not going to be important. 99% of the time, you're going to study integers, and then rational numbers, well, to a limited basis, because after all, rational numbers are integer over integer, so the properties of integers are, and many of them are actually carried over, and they're related, so in that sense, we study some rational numbers. Pretty much everything here is going to be integers. Even for rational numbers, those relate is directly to integers, to the numerator and denominator. Okay, that's it.